Alright, this is a video presentation for ECE 416, Introduction to Neural and Adaptive Systems at the University of Missouri, Kansas City. Commissioned by Jesse Lowe. So we'll get started here. The first one is the, I guess kind of we'll talk about what the actual goal is of this project, which is to take a data set from a surveillance video outside of a store, be it like a JCPenney's or something like that. And they want to analyze the outfits of their customers, and then kind of keep in stock more of what they think people are going to purchase. Well, I'll just run this one so I can get the other result. So the idea here is that we want to set up a multi-layer perceptron to identify out the different symbols, like say Michael Jordan's numbers on a hoodie or basketball jersey, and then also symbols like the Nike swoosh, and then on a separate MLP, multi-layer perceptron, we will try to distinguish if it's a sweater, or if it's a hoodie, or if it's a pair of high heels even, I think I saw in there. And then use that combination of knowledge to find out what people are wearing outside. So this is the topology of the first NMIST data set here, which is the numbers. You can see that it only trained for about, well, exactly 6. That's kind of weird. Let's run that one more time. Oh, it's still 1 second on that while it finishes thinking up. So this is the topology. The topology is how the network is set up. You can see that this one exists of 3 hidden layers, with the first hidden layer being 30 nodes, and then 38 nodes, and then 51 nodes. So the idea behind that was initially you just kind of picked them randomly, and then went back and I decided to do something a little bit different. I decided to use more of a sample. The samples, I mean, divided by the number of inputs and number of outputs. It was a formula we talked about in class, and I used the floor function here to make sure that it is a actual integer, because if you pass in a number like 1.3 to the NMIST, it will freak out and blow up and melt your computer. So A here is my scaling factor, put it as 5 for the first layer, and then 4 for the second, and then 3 for the third hidden layer. Number of samples, our inputs, our outputs, all that good stuff. So our inputs here comes from this. There is this right here, 800 or 784. That's where that comes from, and then the number of outputs here you can see over here is 26. Right now my training ratio is 70%, validation 20, testing 10, and my learning rate is 0.001. The epochs I set as this formula because the idea is that as I increase or decrease, or rather as I decrease my learning rate, I don't want to stay at a super high epoch, because it's going to make your trainings take longer and longer and longer. And then again, this is the data set of the first NMIST. See, it's just like a bunch of handwritten digits, maybe here an A on the side and stuff like that. From there, we kind of played around with these, and I just changed these values on the fly because the fact that we had to drop in and take out hidden layers, put hidden layers in. There was no easy way for me to iterate through that in an autonomous way. But you will see here on the fashion script that I did things a little bit differently. So what I did here is I set up all my variables in matrices. So I have 4 learning rates and 4 training samples. This is kind of my label network, and I'll explain that a little bit later. Then I load in my data set, which you can't do the first time, but after I've saved them all down here in these, if I want to load in and just run one of them, which you'll see in a second, I want to load that data in. So then I prompt and I ask a question if you want to continue and start in at 1. Again, that's just a variable for right now. And then for these 2, I find the length of my matrices, which I could just put them in, but I like to leave them as kind of the variables. That way if I go in here and I add an extra training function or back propagation function, then we will not have to change this value as well. Also note here that the training LM function is terrible, and it melted my computer 3 times. If you try to use the training LM on this function, it will just lock up, send your CPU to max, send your RAM to max, and I have no idea why. I imagine it has something to do with the fact that we can see the difference between these 2 here. This one has, I believe it's a greater input pixel density. I think this one is like 25 or something, and this one, before it's trimmed, is like 256 or something. But I'm not positive on that. Excuse me. So since that has to back propagate more nodes and whatnot, it takes longer. That was my guess. Could or could not be right. But moving on. The first iteration loop is for the training function, where I set my training function. I index the matrix here. So for the first loop, it's this one. Second loop, third loop, fourth loop. I clear my if statement check, and then I load in all my values. So my learning rate for this loop is the learning rate of j, which j is in the first case 1, which makes it 1 here, so on. Epochs, I again do the formula for my epochs, because as I decrease my learning rate, I want to decrease my epochs as well. I set, these are just names, creating variable names, so that when I save it, I can save this one as tr.tr1 for the first one, tr.tr2 for the second, and so forth. And the same for the x data and the y data, which the x data is, I believe, the targets. Let me just check real fast on FashionNet. Come back here. Oh, also, while I'm here, I did change this into a function so that I wouldn't have to keep coming back into here. And x is going to be the labels. Okay, so that is your targets, and y is your output of the network. Okay, so I think we talked for long enough. Let's go ahead and see this sucker in action. I'm going to run it. It's going to ask me if I want to run the first network. For the sake of the demo, we'll just say yes, and it pops with a function. Great, I broke something. Let's see. Oh, that's because MS is not in here. Okay, I can fix that. 1 second, my apologies. So we are running fashion function from. Where's the factor? Fashion run. Okay, so let's come into here. Oh, come into here, and we need the read. Need these 2 guys right here in order to run that one. So we're gonna copy, move it into here. I kind of have them all separated, and it's good for me to see, but bad for the program to run. So try it again. All right, so while it's thinking, let's go ahead and talk about kind of what happens here with the back propagation. So we have a number of inputs, 784, that get fed into these 30 nodes. Each one of these inputs is connected to all of these nodes. and each one of them has a weight and a bias. The biases is normally set for the hidden layers as entirely, and the weights are adjusted as it back propagates. So, all right, so we got done here, and you'll see it says, do you want to run net2? Just for efficiency's sake, we're not going to run through the rest of these, although, let's see. So the last number of my student ID is 5, so I think I'll go ahead and do network 5, but not the rest. No. It's not saying the name of them either. I should fix that. Okay. Come back in here. Why is it not saying %D? Let's try that. That should have fixed it. So let's try this again. Okay, we're gonna skip the first one this time. Well, that wasn't supposed to happen either. We're just having all kinds of fun right now, aren't we? Okay, let's do. Let me just see what is net right now. Is net. Oh. Next num is what this is supposed to be. A little bit of a spoof there. All right, final time. We can see some troubleshooting in action here. See what happens. Okay, network 2. We're gonna skip that one. Skip that one. We said 5 is what we're gonna do, so we're gonna run 5. I think after this we'll try to conclude here, but I will pull up this little report right fast. So the abstract is just talking about what we just talked about, that we're trying to classify clothing outside of a clothing store based on camera footage. This is the network topology for the first one. This was my first ROC curves. They actually looked surprisingly good for the default run, and there was only a few setups that didn't look this good. From there we have just talking about the process, which is where we set up a neural, a multi-layer perceptron with some default values, then we run them over and over again, and then I used this formula for my hidden layer size. So this first curve is the first ROC of the first MNIS function, and this is the one that we found that was good. You can see that it's kind of really close, a lot closer, I'm sorry, to this x equals y line. This x equals y line is the line of complete indecision, so I toss a coin, it's 50-50, I have no idea what it's doing. And then the farther it gets up here towards the 1 or the false positive is good, because if it's all the way down here, I just have to flip my signs, right? If I know enough about it to predict that it's not a tails every single time, I at least know something, and I can say, okay, if I just change my prediction to it is a tails every time, then I'll be right. And we see here we have 26 classes, which coincides with the 26 different symbols, letters we saw, like the A on the side and stuff. And then our references in here we have, well, that is an example. But we have the Goodfellow book, and then the Neural and Adaptive Systems book, which I found to be a little bit more useful. It had more pictures and kind of helped explain the networks, whereas the Goodfellow book was just all 100% the math, what it's about, and all that good jazz. Oh my Jesus. So this is still training here, but the idea is that we iterated through and we will train a whole bunch of different networks, and then I save, at the end of each loop, we save all of them here as structures. So we look here, I'm saving nets. So if you come over here and we look at nets, where is my nets? Here's a nets, it's a structure. and the structure contains structures, and each structure is what this code, which is it takes here, it trims the pixels, it resizes the image, it sets the number of samples that are available, and then this one here, it takes the read vectors file and it returns your images and your labels. It reads just your image UByte and your labels UByte. And then of course some relabeling here, some dummy variables, sample array links, your input values, and then your train labels, hidden layer sizes. Because for the purpose of this script, we were not changing the hidden layer sizes. Training function, which we pass through as one of these four. We use pattern net here, hidden layer sizes with the training function. So this pattern net is what creates this topology and gets it all set up to train. And then we set all of our divide parameters, which you can see this net right here is a structure. This structure is what I return. So if we look over here at these nets, now that it's done, it might actually open up. Maybe not. So I'm gonna go ahead and skip all this because the video is getting kind of long here. So skip the rest of the networks, and it'll load up all of these. These here are the performance curves of the networks, as opposed to these here are the ROCs of each one. You can see some are kind of bad, others are a lot better. And just going through and kind of plotting all those side by side, we can see which ones are the best. And then here, like I said, nets is the structure we're saving, and inside each one is another network. This here is the network. I should be able to just do view net.net1, and that pulls up this topology. And I can do that for each one to see what the topologies look like. But again, we didn't change the topology in this example, so that's pretty much it. I'm trying to talk as fast as I can, but 17 minutes really sneaks up on you here. So I'm going to try to get this finished and submitted. If you have any other questions, comments, concerns, just feel free to let me know. Have a great day.